Okay, do you guys remember the setup of massively parallel algorithms? So I'll just write MPC for short. Okay, massively parallel algorithms. So the point is that we have some lots of machines, but each machine is not strong enough to handle the whole inputs because the input is super large, right? And we assume that input size was n, right? Then each machine's memory size is M, and number of machines is P, right? And you can assume that here M and P both are much smaller than N. Like to be more precise, in particular, M is sublinear in the input size. Okay, for some constant epsilon. Okay, and therefore, so we cannot assume that we can we can assume that you know, no machine can see the whole input throughout the whole process. Okay, so somehow we have to be clever because without seeing, if the no machine can see the whole input, how can you still like achieve what you want to achieve, right? So and the assumption was this, right? The setup was, hey, suppose we have like say p machines here, okay, and in day one, we each machine does some local computation, right? So we assume that each machine has some local like input, right? It works only on the work, on the local input. And then during night, it communicates, right? So some like some part of data is goes moves to the other machines and so forth. And then we assume that every machine can send and receive up to m units of data. And then our goal was to like minimize the number of rounds. So a pair of day and night is called a round. Okay. So remember that in the nighttime, there's no local computation. So in daytime, every machine works harder. Every works only using its own input. And then in nighttime, it communicates and it repeats. So how many times we need to repeat this, right? That's the complexity of this, round complexity, which we want to minimize. Okay. As a warm up, we first saw like counting the frequency of words, right? That was very easy. And then we saw another example, some warm up example, like a minimum span tree, right? So we saw top K, elements, and then we saw like minimum span tree. Okay. And then today we are going to see another example, K center. Okay. Before covering K center problem, I want to briefly review minimum span tree topic because it seems that many of you haven't learned the minimum span tree in your undergraduate. Uh, so I want to briefly cover that. And I think it'll be useful because I can use it same problem minimum span tree as an example in chapter 4. Okay, but I spend only like 10 minutes usually. But if you have any questions, you can stop me anytime. Okay, so let me just stop sharing this, and then I'll share a lecture note with my computer. Oh, excuse me. So actually, I this already. Can you see the screen? Okay, so um, yeah, so like let me briefly remind of you in this problem. So we are given undirected graph here. So like here every edge has some certain weight. Okay, and we want to choose, we want to find the subset of the edges, right? So that that connects the whole that spans over all the verses. Okay, and there are like a couple of algorithms, a cross-cultural algorithm, Prim's algorithm, and I want okay, I'll just briefly talk about the algorithm and the key idea in the algorithm. Okay, because we will use that idea. Okay, in cross-cultural algorithm, what you do is this, right? We are going to sort the edges in increasing order of their weights. So, you see this at CDF, right? This is the cheapest edge. This is the edge with the low, the smallest weight, right? So we choose that, okay? And then, okay, next edge two, this is, I can add that. Okay, I just want to ensure that, create no cycle, okay? And then next one is three, and next one is four, and five, six, and seven. But I cannot choose eight here because if I would choose eight, then one to eight would create a cycle. Okay, so I don't do that. And then choose nine, and then don't choose 10. Okay, because otherwise I would create a cycle 4, 7, 5, 9, 10. Okay, so don't choose this one. And then 11 again, no. 12, no. 13, no. 14, no. 15, no. But that's it. So you can easily see that this is a spanning tree. It's a tree, and it's a spanning tree because it spans over all verses. It connects all the verses. Okay, and furthermore, this is a minimum cost spanning tree. This is one of the algorithms, popular algorithms used for finding minimum spanning tree. Okay, I'm not going to cover in the data structures here. Here, the key idea is the following. So I think it's here. Okay, let's assume that the older edges will have different weights. We can make this assumption WLOG by breaking ties arbitrarily, consistently, or by perturbing the edge weight slightly. But anyway, this is not a big deal, but this will make the exposition much more clear. Okay. And then again, I just want to have like two definitions here. So uh, so we say edge E is a safe if it is the cheapest edge crossing some cut. Okay, so remember what cut means, right? So you run the global mean cut, right? So cut is nothing but a partition of the whole vertex set V into two partitions, right? For example, S and V minus S. Okay, so let me give an example. So let's see this one, right? So let's look at this partition, right? This is one side, say S, and this other side, V minus S. Okay? And then you see there are three crossing edges here, 3 and 13 and 12. Okay? Among these, 3 is the cheapest edge crossing this cut, right? I mean, this is cut, right? So so therefore we can say that this edge CD is safe. Okay, so again, safe means that it's cheapest edge crossing some cut. Okay, so okay, now let's look at another example. So, okay. So for example, like say this edge, A and B. So the question is it safe or not? Safe means that if you believe that this is safe, you need to give me a cut, okay, such that the edge is the cheapest edge among all the crossing edges. Okay, so because this is a first example, so let's just I give you one actually. Let's think about this cut, right? A and all the others. There are only two crossing edges, right? AB and AB and AH. So AB is cheaper, just cheapest edge crossing this cut. Therefore, AB is safe. Does it make sense?
Yes.
Okay. So I just ask one more question and then move on here. What about now? Six. It is safe. So to show that it's safe, you just need to find the one cut.
So we can go through 11, 6, and 12.
That's right. Good. Excellent. So if you think about this cut, right, then 11, 6, 12, these are the crossing edges, right? And 6 is the cheapest. Therefore, this is safe. Okay, by the way, this doesn't mean that it's cheapest crossing edge for every cut. For example, if you think about this cut, right, C and D, all the others, 6 is not cheapest, right? So the definition again, I just show the definition and then move on. So edge is safe if it's the cheapest edge crossing some cut of the graph. That's the definition. Okay. And like the beautiful theorem is this, right? So okay, so this we can this there is a unique minimum span tree if you assume under the assumption that all edges have distinct weights. Okay. And then very interesting thing is that the edge E is the minimum span belongs to minimum span tree if and only if the edge is safe. So in other words, this safe edge definition completely characterizes the solution. So if you know the edge is safe, then you have to choose. You must choose it. If it's not safe, you must not choose it. Okay. And what you can do is the following. So last time we argued this, right? So I just wanted to cover this. So an edge is not safe. Okay, I want to actually show this, right? An edge is not safe if and only if actually is okay. I first write this one. An edge is not safe if it is the heaviest edge in on a cycle. Okay, so what does this mean? Okay, so let me give an example. So in this picture, okay, So let's think about, for example, this cycle, right? So 8, okay, so if on this cycle, there are 3 edges, 1, 2, 8. This is the most expensive edge, okay? Then it's not safe. This is why this claim is true in general. So in other words, if you have a cycle, okay, if you have a cycle, and then if you see on like a very expensive edge on the cycle, then you should not choose that. Actually, you can safely discard the edge. This is why this claim is true. Actually, let's think about more interesting example. So, for example, let's see. Now, let's look at this as this instance, this cycle. Okay, this is another cycle, and you see that 15 is the most expensive edge on the cycle, right? Okay, and then why is not okay? If it's not safe, then it means, by definition, E is not safe. Means that is not the cheapest crossing edge for any cut, right? So why is the case? Like think about any, okay, so I'm looking at this H and I, right? So think about any cut that separates this. For example, think about this, right? Okay. Then what do I know? Okay. So I'm looking at, both sides, right? This is side one and this side two. Like these are different sides because I belongs to side one and H belongs to side two. Okay. This cut separates I and H. Okay. Now what's happening here? The cycle, if you look at the cycle here, it's a cycle. So there must be another edge, right? That crosses this cut because it's cycle. So in this case, this is another edge that crosses this cut. Okay. And this was the most expensive edge. Therefore, the another crossing edge must be cheaper. Therefore, 15 cannot be the cheapest edge, cheapest crossing edge for this cut. Actually, this is true for any cut that separates an I and H. Okay, so that's the thing. So if you find any like the heaviest edge on the cycle, just remove that because it's not safe. Actually, you can show that this is if and only if. I'm not going to prove the other direction, but it's also true. So to remind of the algorithm we studied last time was the following. So in studying minimum span tree, what did you do, right? So we partitioned edge set. So we were given graph, right? And then we partitioned the edge set into P machines, E1, E2, like EP, right? And then what did you do? We ran any like our favorite algorithm. You can, for example, you can run algorithm, Kruskal algorithm or Prim's algorithm to compute the minimum span tree on the set E1. So we actually just run. So we still keep the older versions, but we only have a subset of edges. Okay, and then we get a minimum span here, minimum span here, minimum span here, and then we aggregate all the outputs right here onto one machine, right? And then this is us, and then we run algorithm again, right? And that was it, and that was the idea. Okay, And again, the key idea was that, hey, whenever we discard it, so if edge E is dropped here, if E is not safe in graph, right? So this means that E was the most expensive edge on some cycle in edge set E1. Okay? And what does that mean, right? Then it means that E also is the most, some cycle say like C is the most expensive, right? H on same cycle C in the whole H set E. Okay, this implies that E is not safe. Excuse me, not safe in the original graph. So whenever we dropped edge, we ensure that we only dropped unsafe edges. We never lost important edges, right? Okay, that's it. This is a key idea. If you have no more questions about this, I'm going to move to the next example. Is it fine? Any questions about this? It's good?
Yeah, yes, it's fine.
Okay, great. Okay, so let's move to the next example, the final example in chapter 3, which is K-center clustering. Okay, so let me remind of the setting here. So this notation is different from what you learned, what you used in the previous lectures, because I'm following the tutorial here, but the problem is the same. So K-center problem is kind of simple clustering problem. Okay, so what are you given here? X is point set. It's an input point. Okay. Here, we have like n points here. I mean, in our case, we use this. We see here, n points here. And then we are also given metric. Okay, these are in metric space. Metric space means that this y, this is 0 at the distance between the two same points y is 0, and then it's symmetric. And it satisfies a triangle inequality y, xy plus d yz is only greater than distance between x and z. Okay, and then our goal was the following: find the choose a subset you want to choose k points, right? Such that the distance between, okay, so we want to minimize the maximum distance of every point here. So we want to okay. So as before, we are going to define this d. We can extend the distance definition to distance to a point and point set. So this definition is defined as the minimum distance between between any point in C and V. Okay, so remember this problem, right? So we learned that this is, there is two approximation. This is right. And we also showed that it's NP hard to get better than two approximation. Okay. Yeah, so here, so we are going to same thing here, so as before, we are going to given person set X, we are going to split X into P groups. Okay, so X1, X2 through XP. Okay, we call that P is sublinear in the input size, number of points here. Okay. And what do you do, right? So let's say that, we learned two different algorithms in classify. So say, choose anything. Like you can use, let's call A, call the algorithm A, okay? So it can be Davis-Moyes algorithm, or you can use Gonzalez algorithm, whichever you like, doesn't matter. Because we are going to use the algorithm as a black box. We're not going to open up the implementation, okay? So what do you do? So like given this X1 on each machine, we are going to apply this algorithm and we'll get K points. Okay, this is a two approximate solution for the partial input X1. So all these computations are done locally. Okay, so when you run A, the same algorithm on this, same algorithm on this partial input X1, it doesn't need to look at other, other partial inputs. It only needs to look at this X1 and outputs K points. Okay. And then, so what do we do? So let's call this Y1 for simple, notation. And then, what it did was that, hey, let's dump all this Y into single machine. So, and we run. So this machine will now have Y1, Y2 through YPY. And we run this algorithm again on this. Okay. By definition, the algorithm will output, K points, K centers, right? So K center 0, K center 0, K center 0. So when you aggregate this, we'll have a K times a P points, right? And by running the algorithm, finally, we'll get K points, K centers, okay? And we return this as our solution. And the question is that how good is this? Are we using, does it, are we actually, do we actually meet the memory requirements? Okay, those are two questions. Okay, first let's see the memory requirement. Okay, so okay, this we have endpoints here. Now here, because we split these endpoints across into n p groups by equally, so each machine will have will be given n over p points. Okay. Now of course now each outputs k points, k centers as output, right? And then here as you argued, it's kp points, right? And at the end of the day, we have k points. Okay. So Okay, we are going to set this P, let's say the P is squared n over K, okay? Then P over K, n over P becomes what? It becomes squared times NK, right? And this KP also becomes squared times NK, okay? So you see that P, and we need to ensure that and P and is here. Every machine here used up to skirt NK skirt NK, skirt NK memory, right? So we need to ensure that this both P and M. Excuse me. We need to ensure that P is much smaller than N. Also, we need to ensure that memory size, this is NK, is much smaller than N, right? Otherwise, there's no point of using this, parallelism, right? Okay, good. So like you can see that here, M, the memory size here, assuming the K is small, it's typically small. Like that's the whole point of using clustering, because when you are given lots of points, we want to summarize that into a small number of points. So K is much, excuse me. So K is much smaller than N. And under that assumption, you can see that M, the memory usage per machine, is much smaller than input size. So this is good. Okay. And then the next one, well, I mean, P, right? The number of machines is also, M was squared N. So it's a much smaller than, input size. So we're like, so, okay, we use the sublinear number of machines, and we use the sublinear amount of memory per each machine. So which is good. Okay, now the remaining thing is to show that this algorithm is actually good. So we want to show that. Okay, I'll just a different next page here. So we're going to show that this, we want to show that this algorithm is A approximate. Okay. If you're careful with care, for approximation, we can show for approximation. So the analysis that shows the algorithm is A approximate is not tight, but let's not worry about that. Okay. So because the idea is more important. Okay, so what do we have here? Okay, again, this is the picture. Let me copy this again. X1, X2, and there's Xi, and there is XP eventually, right? There are P groups of machines, P machines. Yeah, and then what do you do? So actually, let me slightly modify this notation here. Suppose it outputs C1, C2, and might use Y, but let's just change this notation here. Okay, and then now this. Okay, and then we aggregate all these, right? And then suppose it outputs C. Okay, so we are interested in understanding how good this solution C is. Okay, so recall that our goal is to show that is A approximation. Okay, so let's say that opt is the optimum objective. Okay, and then our goal is to show that is is this. Namely, for any point, we want to say that there is some point we have chosen, right? That is within distance A times optimum. Okay, that would imply, this algorithm is A approximation. So okay, so how do you show this? It's kind of simple here. So before doing this, let me make one simple observation. So let's think about any like a subset of X. Okay, and then let's use like opt Y to denote the optimum for this Y. Okay, so opt is nothing but opt XY by definition. So in other words, opt Y means that, hey, let's only look at the subset of points here. Okay, and then what's the optimum solution? What's the optimum objective? That's what opt Y means. Okay, and I have a question for you here. So is this true? Opt Y is at most opt. If you want, I can just put it here, X here. Do you think this is true or not? So on one hand, so you can say, hey, well, I need to like, I have only a fewer points to cluster. Therefore, hopefully I can do better because I don't have to cover all the points, right? So in the sense, maybe opt of Y can be smaller than opt of X. However, there's a disadvantage because now you can only choose points from Y. Okay. If it's a Euclidean space, then where you can choose any point as a center, then this would be actually true. But now you have to choose only from set Y. So let me give an example. So think about this Y. So there are, could say 3 points here. Okay, say K equals 1. A very simple case, Y. Then, and the distance is 1, right? So this is like A, let's call this A and B and C, right? And you see, opt ABC is just 1, Y. Because if you choose, I'm K equals 1. Because if you choose B as a center, every point ABC will be within distance 1, right? But now imagine that you just don't think about this B, right? Then you're only left with A and C, right? You cannot choose B anymore. Okay. In this case, the optimum is 2 because you are forced to choose A or C. In any case, you have to pay cost 2. Okay. So this is not true. This is not true. Okay. Opt of Y may be bigger than opt of X. But what I can argue is that actually, if you're, it's within still factor 2. Okay. This is why now. Why is it still like within factor 2? This is a helper claim. So the reason is the following. Okay, think about like X here, the whole set X, right? So like, think about this optimal clustering, right? For X. So it has chosen some center. Okay, let's, I'm going to draw squares to denote the centers in the optimal solution. Okay, then it means that, by definition, it means that like every point y is within distance opt from the centers y. Okay. Yeah, but the problem is now, okay, so if you look at y, I mean, you may not be able to choose this anymore, right? Okay. But however, for each cluster, you choose any point as a replacement. Like I say, like this triangle. Okay. Then what I know is that, hey, this distance is at most opt, right? And this distance is at most opt, right? By triangular inequality, so every point in this cluster is within distance twice optimum from this triangle. Okay. So therefore, like by choosing any like arbitrary placement in the cluster, you can still find the clustering whose cost is almost twice the optimum. Okay, so to recap, so for any subset y, any subset y of x, we are guaranteed to have that optimum of y is almost twice of optimum of x. Is it clear? Okay, so yeah, again, if you have questions, please stop me, okay? Otherwise, I have no idea because I don't see your face, so I cannot really read from your face, right? In person teaching, I can see, hey, if you're getting, or if I'm losing news, but in remote teaching, I have to I need some feedback from you by chatting or something like that, okay? Otherwise, just I'll lose you. Okay, good. So what do we do now? Okay, great. Now we are kind of with this helper claim, we can actually prove this our main goal, namely the algorithm is A approximation. Okay, we are going to show that by showing for every point is within distance A times opt from our solution C. Okay, so like consider any x, any point in x. Let's fix it. Okay. Okay, then it means that because we partitioned the whole verse set into p pieces, right? That means that x must belong to some xi. Okay. So okay, good. Then let's say that okay, I'm going to zoom in this picture because it's a bit small. So I just did the big picture because otherwise it's hard to see. This is xi. Okay, so I'm looking at some point here, x. Okay, so what I know is that hey, so we chose ci as a partial as a case as a solution for xi. Okay, so then what I want to know is this, right? What's the distance between x and ci? Okay, so we have chosen some centers here. What's the distance here? Okay. Well, remember that we use two approximate algorithms. So it'll be twice the optimum of xi. Okay. This is a subproblem line where the point set is only xi. Okay. And we used a two approximate algorithm to solve this problem. And therefore, every point, particularly x, must be within distance twice optimum of xi. Okay. From the solution ci we have chosen. but we observe that opt of xi is n most twice optimum. So it'd be n most 4 times opt of x. I mean the opt, just opt. Right? Great. So let's say that okay, then okay, in other words, so if I write this, because it's a distance between x and subset versus ci, so this means that dxz is 4 times optimum for some z in ci. Okay, this is just by definition, right? Okay, now we are almost done. We want to know what is distance, right? What's the distance from what's distance of x from C, our final solution. Okay, so let's just start to take indirect root here. So by triangular inequality, we have the following. Okay, and then we already argued this is because triangle inequality. We already argued that distance between x and z is n most 4 times optimum, right? And what about this, right? Again, this. So what's z here? Like here, the input was C1, C2, like all like CP, right? So input included the Z, right? Because Z belonged to CI. So therefore, because we ran two approximate solution for this subset, okay? So it must be at most twice the optimum of C1, C2, CP. Again, this is a subset of the whole versus set. Therefore, I can use this, helper claim and to conclude that this is at most 4 times optimum also. So in total, it's 8 times optimum. Is everything good or no? Do you have any questions about this? So we argued that we don't use much space on each machine, so which is good, which is the whole point of using massively parallel algorithms. Secondly, we show that hey, even though like we kind of use kind of divide and conquer algorithm, so we can still get reasonably good approximation. Okay, so if you don't have any more questions, I'll just briefly talk about like core set. I don't want to go into details because it's a bit heavy topic. Core sets are very popular in clustering. So yeah, although like all the examples are kind of like we use the same algorithm, on each partition as a black box. We can think about different idea. Okay, so like here you only discard some points, right, and took a C1. But you can it's a core set is kind of sketching. Okay, so now think about like say K center in Euclidean space. So the everything is the same as before. So namely, we are given input points at x, and we need to choose k centers. But now, k centers from the Euclidean space. So you don't have to choose the centers from X, the input point set. No need to choose points from X. That's the only difference. Okay. Then because we have more freedom, and actually we can do better. We can actually get so what's the idea here? Like I'll just give you a sketch of the idea. So when you partition the input into like multiple pieces, right? X1, X2, and like XP, right? Okay, so we have like some partial input here, XP. So what do we do? So before we just ran like, I was two approximation algorithms and we up like A of X2, and we just obtain the K centers. Okay, let's not do that. So like what I'm going to use that. We're going to summarize this X2. So like what do I mean is the following. So we're given like a bunch of points here, right? Still many, although like we kind of dwindled it by, because it's only a portion of the whole set. So what do we do? Well, like conceptually, we can kind of, build a grid. Or maybe this was not a great example. Okay, sorry. Let's maybe. So maybe this is a better example. Okay, good. So we're going to some conceptually build a grid. Okay, so then what do we do here? Like you see, these, for example, these 3.5, they are so nearby, such that they all belong to the same cell. Okay, so okay, I don't, in K center clustering, I don't care about the number of points here, right? So if they're like tens of points, like billions of points at the same location, I don't care. Okay, so what I'm going to do is that I'm going to keep only one point here. Just drop everything here except one point. If you want, you can even move to this to, you can pretend that it's just it is somewhere here. Anyway, the point is that because all these points are in the same cell, they are far from each other. So now after the simplification, what do I have is, hey, I have only one point here. That's my summary. And likewise, okay, there's a 1 point here, 1 point here, 1 point here, and 1 point here, 1 point here, 1 point here. Okay. So by doing that, I can, I kind of summarize the sketch to the input here. Okay. And then like I grab like all these summaries right from the machines and dump into one machine. And then we can run this greedy algorithm. Okay, you see the difference here? Before, we actually chose only K centers, K points on each machine. But no. I mean, I'm okay to use slightly more. I'm okay to output more points. Okay. But here the point is that I want to ensure that I don't lose much, because before I lost 4 approximation or 8 approximation. But now by outputting more points, and by constructing put refined a grid, and I don't lose too much. Hey, yeah, sure, I lose something because for each cell, yeah, I don't keep all these points location, but I only keep only one, and then I pretend that all these points have the same location. Because of that, we have a loss, but not much if we build this grid pretty much in detail, right? And using this idea, you can get like you can improve the approximation. You don't have to do the 4 approximation or 8 approximation. Okay, so this idea is called a core set. Okay, so you can decompose, and then and then run some summarizing algorithm to make it compact, and then aggregate them, and then you solve the problem. Okay. If you're interested, you can read the last chapter, the last sub chapter in chapter 3, and it talk about core sets. Core sets are used actually for like other clustering problems, for example, k means or k median, which I didn't cover in this class. But I covered, for example, k means or median or k means in approximation algorithms. They're like we also use there are lots of core sets algorithm. So if you use core sets, you can like summarize a big input into small subset, and you can run the algorithm on the small subset of points, and therefore you can compute the desired cluster, approximately good cluster result fast. Okay, let me stop here, and then we are going to have a like 10 minutes break before moving to next chapter 4.